casual meeting. Very low key this one.
Nice weather.
Yeah, it's the weather, exactly. I think so. Thank you for those who made it. We have a great speaker tonight, Robert Musson. Works at Microsoft in the Skype group. He has a really compelling talk, I think, about how data science is changing software testing. And I'll leave his credentials as usual. And at the end, we'll have a little door prize drawing. Maybe tip you up on that, Robert. You're the drawer.
Okay.
The award giver. So welcome. Thanks for coming.
Okay. So as I said, I'm Bob Musson. I work at Microsoft. I work on the Skype team. I actually work in the Link product, so it's part of the Office package if you're familiar with various Office products. And I'm a data scientist there, and I spend most of my time, I would say, just looking at numbers. So seeing the matrix where it just looks at the numbers coming down the screen, that's what I do. I stand there and stare at the various numbers. So what I'm going to talk about tonight is I'm going to talk about some of the current issues that I see going on in development. And a lot of this, of course, comes from my perspective at Microsoft. So you'll see, some of the things that we're doing and we're starting to do different in development as opposed to what happened, let's say, 20 years ago, 15 years ago. Even as recently as, say, 5 years ago, you still saw very similar development cycles to what you had 20 years ago. In the last year, 2 years, let's say, in that time frame, you're starting to see very different ways of developing software. And I'll talk to that. I'll then talk to some of the data science skills that you need and the reasons for having those skills and where I believe test is moving to and how we're going to, in the future, work as testers. And then I'll talk a little bit about what I think the new quality work looks like. So I've been around about 25 years, so in my day, and of course, ones that we're used to, okay, we've heard it all before. I walked 10 miles to school, uphill, both ways, and it was always snowing. I'm from Chicago. Well, in a sense, that's how it was. So how was it really? What did we do differently in those days? And why is it different nowadays? Why are people saying these things? Well, okay, the test team, at least the test teams at Microsoft, are now called quality services teams. So there we have it, difference. Any questions? That's all I got. Okay, that's, of course, hopefully there's more than that. But one of the things that we see is that in the old days, test found bugs. That's what we did. We were quality control more than quality assurance. People would wave their hands and say, oh yeah, no, we're quality assurance. Nobody knew what that meant. We're quality assurance. But in essence, we found bugs. That's what we did. Developers wrote the bugs and we found the bugs. That's kind of how tests worked. And then we moved to these multi-year development cycles and we had these really long end games in our test. And the reason for that was because everything was in a shrink-wrap box of software. So there was no way to upgrade the software once it was out there. At least, let's say 20 years ago, then we created something called Windows Update, so at least you could get patches, and we still didn't have a good way of deploying it. So a lot of the assumptions in the development cycle were based on this knowledge. And the knowledge that I was going to spend 2 years, half of that was going to be in the development cycle. And so that made data gathering really easy. So one of the base assumptions, every build is better than the build before. Mostly that's true. Put it in data science terms, we were a non-homogeneous Musson process, and we could make assumptions associated with the sub-additivity process and increase reliability based on that. Now, of course, every tester knew that, right? That's what they were doing. Probably not. They probably didn't understand the process dynamics, and they probably didn't understand what theories they were using in their data collection. But the fact is, they were using this sub-additivity process. And they were, in fact, able to use the base assumption that every build is better than the build before in order to do their work and to get their metrics. makes things really, really simple. So, some teams might show up as counting test cases, counting bugs. If you were really not enlightened, you probably did things like code coverage. But all of those metrics sort of worked in the old development cycle. The problem is, we're not like that anymore. Okay? Nowadays, we have these things called Agile methods. And in Agile methods, you release, let's say, every month to the customer. You're constantly adding new features. You're still a non-homogeneous plus-on process, but your time is different and your event horizons are different in that. So you can't solve a simple equation and then say, I can look at the bug discovery and say, that's how I'm going to determine when the software releases, because you're constantly adding more bugs to it. The fundamental assumption of the software is better in every release is no longer true. That wipes out every metric you've ever heard of from the perspective of test. So the minute you move to Agile methods, stop measuring anything that goes with test because it's just invalid. One of the other current issues for test, of course, is services. And in services, we release a lot of time. Okay? And on top of it, you want to be able to release immediately when you find a bug. So you find a bug, you fix it, you release software absolutely immediately. So there is no test cycle in that case, right? We've shrunk the test phase to 0. However, we have not shrunk the bug count to 0 simultaneously. So we had some more new issues with it. Another issue with test is the so-called big data. I kind of hate that word, but we have all the data flowing in to us. That's actually a problem for tests, because they've got to use it somehow. So they'll end up using it badly, and I'll show some bad uses in a minute. And what we want to start doing is using it correctly. And then finally, of course, the other issue for test is human error, and I'll talk to that in some of the data in a minute. So let's think about bad science, bad data science. What does bad data science look like? I always like to look at what a mistake looks like, because I know I'm going to make it, so at least then I'll identify what it looks like. And I'm going to start to show some really bad mistakes. I might have picked some not the greatest examples for these. But here's bad science. Okay. I happen to use, this happens to be a site that just goes out and looks for spurious relationships between data. Okay. So it turns out, this might not have been the best example I picked. It's a little bit dark. But turns out divorce rate and murders are highly correlated. Again, R squared is 79.79. R squared, in essence, for a two-variable model like this, R squared is the amount of variance in the data explainable by this data model. So you got roughly 80% of the variance explained with these two variables. Boy, hey, maybe we shouldn't let people get divorced, or we should make everybody get divorced, or whatever it turns into. Of course, that's nonsense. But that is bad science, and we see it all over. Here's another fun one. This is kind of one of the reasons why we have to protect the bee colonies in this country. Okay, because if not, boy, the youth of this country are just, look what's going to happen. Who knows what happens after the marijuana, right? The bee colonies collapse. Every child in the world is smoking marijuana. And then here's my personal favorite, since it is important for me. The number of computer science doctorates as compared against game arcades. Okay. So obviously these are nonsense, and there's the website at the bottom where you can go and see a whole bunch of them. All they do is they go and they mine for nonsense correlations. Look at a little bit more detail. Here's another way of bad nonsense, and that is through hidden dependencies. You can say, oh yeah, we know bee colonies doesn't correlate to that, but we do think that bee colonies in fact correlate to this hidden variable, and that hidden variable then correlates. Okay, that too is nonsense. It's called a hidden Markov dependency in this case, but it's also nonsense. Let's look at the underlying data. If we look at these, we can see, right? If we start to try to explain why these are true, right? So divorced people are going on killing sprees. Boy, with an R squared, with an R, in this case, that's the R value. So the correlation of that is 0.89. So the data is highly explainable by that. And bees keep young people somehow from turning to drugs, right? Because it's a negative correlation, so you've got an inverse there. And then computer science doctorates play a lot of video games. Okay, so no new news there. We knew that one. But As people get more and more doctorates, they seem to play more and more video games. Now these are all nonsense, and as we talk about them, we can see they're nonsense. The problem is, in real data, you don't know it's nonsense. You don't know it's nonsense until you really dig down into it. But you could go through this, and let's pretend they're not these very strange ones that I've created, but things that might sound plausible. Let me pick one that is my favorite to pick on. Code coverage correlating to quality. Turns out it doesn't in any way whatsoever. Every once in a while you get these publications that show it, and we'll show it at what's called a p-value. If you're familiar with p-value, p-value is a level of significance, and typically a p-value of 0.05 is what's used. So it means there's about a 5% chance of making an error, of making a very specific false positive error in that case. Okay. And every once in a while you get a publication that says, oh yeah, code coverage does correlate. And it turns out about 5% of the time you see that correlation. Well, lo and behold, that's the p-value. That's what you expect to see. 5% of the time you get a spurious correlation. But we turned that metric into something important, because everybody in the world measures code coverage. And I like to try to get everybody to stop doing it because of this reason. Okay? It was just bad science that leads to it. And it happens over and over again. But it didn't appear to be nonsense. Somebody published it, more and more people published it, and you add the factor that only positive results get published, so you see it over and over and over again, suddenly it's become truth. That's the problem, and that's what's happening with big data. And that's one of the things that we're going to start seeing. This is another one of my favorites, because this one actually seems plausible. So the number of farms correlates to consumption of eggs. Interesting. Turns out to be opposite, but that's okay. It's a very strange sort of a correlation that I don't know anything about farming. It could happen, right? And that's what we want to start to avoid. And as testers moving into data science, this type of spurious nonsense is what we have to get rid of. So, oops. How do we start to get rid of it?
So you just said there, the opposite could be much more cause-effect than the consumption of eggs might actually.
You might think that's true. Just like, well, if there's more farms, maybe we need more eggs, right? I mean, it makes more sense than some of those other ones.
Yeah, it's supply and demand. I mean, there might be a higher demand for eggs, and then more people go into farming. I don't know.
Yeah.
That site I showed, by the way, is kind of morbid because they correlate a lot of things to death and executions, et cetera, because we got a lot of data on that. So obviously those correlate to nonsense. They're also quite easily, dispelled as being nonsense. Other things aren't necessarily. So yeah, all of these things could be true. We don't know. And I'm going to have to spout a phrase that I also hate, which is correlation does not imply causation. Okay. But I hate that particular phrase too. So I don't want to really put it out there because everybody should know that. So one question is, why is this new? Right? I said a little bit earlier that, gee, I've known for a long time that the test reliability process is in fact a non-homogeneous Musson process. Oh, gee, okay, we knew that for a long time. So why is data science new in this? Well, in the old method, I don't want to even call it the old method, I want to kind of contrast it to business intelligence. So business intelligence, which is very similar to data science, the difference is, however, that data are gathered for a very specific purpose, well known up front. The data tend to be highly structured, and you'll see them in things like SQL databases. So chances are the data coming in from a test process are not in SQL databases. They'll be in Cosmos, they'll be in Hadoop, they'll be in some unstructured format that you're not familiar with. You'll have to scrape it from the web, something like that. So that's one of the obvious differences. The other obvious difference is that the analytics are known up front. So you know up front that a particular thing has to be forced and be true. So something like availability of a service, for example, has to be at 5.9 its availability, whatever the particular availability rate is. So that you're just sitting there measuring it at that point. And if you fall out of 5.9, so you have to refund money, something along those lines. That's not data science, that's business intelligence, it's business analytics. Data science is much different in that it's data are coming in unstructured. Many of the experiments are also analyzed ex post facto. So the data, they are sitting there and I do stuff with them. That's what makes it really tricky. Because one, I don't know how the data are gathered, so I don't have context. And two, I can make all sorts of statistical mistakes on that data. I can't even think how many ways there are to analyze things improperly. And one of my jokes is, we know one way to do it right, we know lots of ways to do it wrong. So that's kind of the difference. That's what we're looking for in the difference between business intelligence and data science. And data science then actually becomes a science. There are some people who don't like calling data science science. They don't see where is the science coming from, where is the experiment coming from. In our case, in test case, the experiment's quite clear. I'm applying the condition and I'm looking for a response. It's very much like medical testing in that regard. So why do we need it? As I say, it's easy to make mistakes with our data. So we need proper science because we don't want to make those mistakes. And I like to think of statistics. Statistics are all about luck. Right? Do I get lucky? Do I get unlucky? Right? How extreme is this particular data set? How lucky have I gotten in gathering the data? And then, as I like to say, every week or every so often, somebody wins the lottery. So obviously, that person is more skilled at picking numbers than the rest of us, right? Or another alternative explanation is they're actually time travelers. They've come back with the correct numbers, and now they're going to go and make a whole lot of money, which was what Warren Buffett was looking for with his pick the perfect bracket in the NCAA. Some things are just coincidence. It is the job of test to figure out what is coincidence and separate that from the real thing that's happening, the actual causation, which is very, very difficult and requires a great deal. One of the other aspects of it that I like to talk about is we are hardwired as human beings. It is in our evolution that we are hardwired to see patterns where none exist. And there's actually quite a good reason for this if we go into history. So let me explain a little bit. This is what's called, the statisticians will call this a contingency table. The computer scientists often call it a confusion matrix. It's just a list of, in this case, what we observe versus what is truth. Okay. So if we have a couple different types of errors then that we can observe. One is a false positive, which means that I observe A, but not A is truth. Okay, so there I've made a type 1 error. It's known as a type 1 error. And I mentioned significance earlier. That's what the significance level is all about, is what's our type 1 error. The other type of error we can make is a false negative, which is we see not A when in fact A is true. That's a type 2 error. And as I am going to contend in a moment, false positives are hard-coded into our DNA. And the rationale for that, actually, we can go and think about it a little bit. If we go back, let's say 20,000 years when saber-toothed cats roamed the plains. So we're walking out in the savannah, we look across the grasslands, and we believe we see a saber-toothed cat. Let's say there is, in fact, no saber-toothed cat. We have just made a false positive error. And we change our direction and we move a different way. Now, assuming we don't run into the real saber-toothed cat, no big deal. All we've done is changed our direction. On the other hand, if we happen to be a human being who is prone to false negatives, we did not see that cat, we stumbled right into it, and we are now out of the gene pool forever. And as we stumble into it, we run away, hopefully, we make it. Most of the time, we do not. So, as a result, that left a preponderance of people who were geared toward false positives. Some people were perfect in their observations, but over time, we began to move more and more and more toward false positives. So as a race, as a species, we are prone to false positives. I would contend all species are prone to false positives because they all do exactly the same thing for exactly the same reason. Now that means that we will see patterns in our data where none exist. And we do it all the time. The case of code coverage is a real good example where we saw patterns where none really exist. And we come to a conclusion that is incorrect. So now it becomes our job as data scientists to get rid of those particular biases. So this, I'm just going to go quickly. Here's 4 of the biases that I think of in test that we have to combat, and that data science is meant to combat. As testers, confirmation bias is the biggest problem that we've got. We run a bunch of tests. Oh, everything works. Ah, okay, it's ready. Okay, that's a form of confirmation bias. I won't go through all these other ones. Here's just a partial list of all the confirmation biases that people go to. This was one website pulling them down. There are a lot of different ways of making mistakes with data. As I said, there is one way to get it right. And the one way to get it right will be the skills necessary for data science. So as we move, as testers, we're moving from test discipline to that of data science. These are all the skills we need. So there's only 2 or 3 PhDs worth of information in there. Everybody can go get 2 or 3 PhDs and then we'll be all ready. Okay. In a sense, that's sort of true, but I don't want to really think of that because I can't. But these are sort of a partial list of the various disciplines that I see adding into data science. Now, early in my career, when I was a lot younger, I did a lot of signal processing. So the type of data processing that you often see me doing revolves around all of the discipline of signal processing. I'll actually look through things like Nyquist frequencies. I'll do all sorts of MMTs on my data, all that kind of fun stuff, because that's my strength. So I tend to work on this side of things versus other people who tend to go more for machine learning. So one of the things that we all need to do is to figure out what is our strength and begin to play to that as testers. Now, Drew Carnley came up with this Venn diagram. I don't know if everybody's seen it or not. It's kind of famous in the world of data science, where in the big bundles of stuff, there are 2 things that testers do very well. One is hacking skills. We know how to really break software, basically, right? We know how to do that. And we have typically a lot of expertise in the area of our software. So the thing that has to get added to that is the knowledge of statistics. And as soon as we get that particular piece, then we'll be able to dispel all these myths that I started talking about. There is one big problem in all of these different fields is you get the synthesis of terminology. As I just said, that one thing I had up there, one group of people will call it a contingency matrix. That's basically, if you hear that, it's probably a statistician who's talking to you, versus a computer science person who's going to call it a confusion matrix. And the reason for it is, well, contingency tables come out of things like logistic regression, whereas confusion matrix come out of different machine learning algorithms. So computer science versus statisticians. So one of the things that we do have to start to bridge is to come up with these multidisciplinary views of the world. Now, I look at like 3 primary areas for the types of skills that we need. First is the data management stuff. I spend over 80% of my time just with the data. Cleaning the data, massaging the data, putting data elements together, figuring out what the data actually tell me. So a lot of that happens to be in the form of exploratory data analysis at times. But a lot of it is just messing around with databases, like SQL databases, or Hadoop, or whatever I happen to be doing, and then cleaning it because data are never gathered correctly. No matter how hard you try, you'll always have that as a problem. Now the good news is a lot of testers are very good at SQL databases. So this then becomes a strength that a lot of us can use in moving to. Then another deep area that people have to get used to is the actual science piece. I try to tell people, ignore the data portion of the data science and think about the science. And when you're in science, you've got to think about the research question, you've got to think about reproducibility of results, you've got to think about what type of analysis I'm doing. Is this inferential? Is this predictive? And that then will form exactly the type of experiments that you can run. So it becomes important then for people to really understand science. Anybody who's got an advanced degree in a hardcore science, like physics or math or chemistry, would be very good at that. So we see a lot of physicists in the world of data science. And then, of course, another deep skill, the one that everybody wants to jump to, is machine learning. I spend 2 to 3% of my time doing machine learning stuff. because just the rest of the stuff requires everything else. And that is the fun part, but that's like another way of looking at it. I think of it in these three layers also, which is the data logistics, which I went into, the analytics, which includes the sampling techniques, and the sampling techniques are also around test plans. So one of the great things about what we do is test is very good at these bottom two layers. They'll have a great amount of skill at being able to do this stuff. And then at the top layer is visualization, where you are communicating your story. Cutting across the entire thing here is a design of experiment, which is test. We already know how to create test plans, which are basically experiments. In fact, we use a lot of the language of design of experiments in the test world. Things like different types of sampling matrices, et cetera, matrices. So this is where test comes in, and it's really the type of thing that everybody can do already. And this is just to kind of give up a few of the tools that I use so that people want to get good at. There's a couple of important tools in the world of data science. I'm going to pick two that are probably the two important ones. If you can only learn two things, I would learn R and Python. R and Python are programming languages that allow you to do a lot of these algorithms. They also have a nice body of knowledge out there where you can go and pull other people's work in. So if I want to do something like a random forest on decision trees, I don't have to write my own. I just go and I load one and I can use it. And there are a lot more languages, and there are a lot more different ways of thinking of it, but I think R and Python are clear winners. I don't remember the market shares for each of those. R was the winner by a lot, and Python was maybe half as much, and then other ones like MATLAB. MATLAB happens to be my favorite. There's an open source version of it called Octave. It's my favorite again because my background in signal processing, and MATLAB is just great at taking signal processing. Then there are also ones for visualization like SAS and SPSS. They're great. Excel fits in there, Jump, Minitab. These are just ones for doing different types of charts then. And one of the important aspects for visualization is how will you communicate information to people who are non-scientists. It's a non-trivial thing to get people to realize that. So these are some of the tools that the testers really should become familiar with. There's also, now, one of the important things, so where I spend a lot of my time is devising experiments and different ways of gathering data. So the mindset difference that I think has to happen with tests is we don't find bugs, we find information. Now in the old days, we used tests to find information, and the information that we found was a little bit, I hate to call it trivial, but it had that fundamental assumption that I talked about, which made the metrics very simple. That is now different. We have to move away from that, and we have to start thinking about complex ways of gathering information. So here are three that we use all the time. So you've probably heard of A/B testing. Okay, I'm going to put two versions of software out there and compare the two against it. But it's more than just two. Okay, you want the ability to pull in, to basically sit there looking at what's happening with all the different versions of your software that could be out there. I have no idea how many versions of Link, for example, could be out there. Dozens, who knows? I can't imagine creating a test matrix that said, I'm going to test all of these combinations of client and server. It's not going to happen, right? That matrix would blow up into the millions of different test cases very, very quickly. But I can sit there and use this concept to look at the data, and I like to think of it as I'm passively looking over someone's shoulder, and I then look at, oh, here's the type of software they're running, here's the server they're going to, they might be on service online versus an on-premises version of the product, and I can gather that information and then do the fun stuff, the machine learning stuff that tells me, look at this, here are clusters of users, these users are getting great experience, these users are, well, not so much. So that becomes then actually looking at authentic user information to figure out where the defects in the product are based upon a particular set of test matrices. Now, what this will usually give is a pointer to the tests you should be running. Okay. So this is then where we link into the existing test mentality. So based on this, I can weed out all of the stuff that I don't need to look at and find only the versions and the different test matrix that is causing a problem for customers. Now, in my case, one of the problems that I like to look at is performance. I want to see, when someone tries to sign into the product, are they signed in under a second or 500 milliseconds? But the typical, whatever the performance characteristic that we want to see. And then I can look at those people who aren't, figure out why they aren't, and then go and do that work. Now, we've always also have heard about test in production and those concepts. The way we would run test in production is you throw bots out there all around the world, and they just start doing stuff. And they're sitting there hitting the product with synthetic transactions all the time. So it's almost like a heartbeat. In the old software, we used to call them watchdogs. So you got a watchdog sitting there doing stuff. In the old days, it was really just a single bit of information to tell me that the software was still running. Now it's all of these transactions should be coming through at a probabilistic rate with a very specific performance pattern associated with them. If that performance pattern ever changes, red flag, and somebody is notified. So these types of synthetic transactions then become a background view of what I should be seeing in the product worldwide all the time. So it's a slightly different use for these two things. Then a third type that we often use is also crowdsourcing, where we ask the crowd to do something. These aren't, I don't know what the right word is, they're not really the authentic transactions of a user, they're not the synthetic transactions of a bot. We somehow incentivize people in some strange way to do something unnatural to the product. And then we look and see what happens. So these are the three types of test methodologies that I use all the time to figure out what's going on in the product and to show off the areas that we really then need to focus on. Okay? So it's all about figuring out where should we be focused, because there's just the test matrix is blown up and there's no time to do it anymore with the new processes. So this doesn't mean that all the old skills go away. Most of the old skills are still there. Things you don't really see a lot of anymore are manual testing. Okay, you don't sit there, hitting the key on the keyboard or installing and removing. So way back when, 20 years ago, there'd actually be somebody, their only job was to install the software over and over and over again from 3.5-inch floppy. So you just sit there putting floppies in and out. Or another one was, we jokingly, we had smart card testing. So, okay, sign in and then pull the smart card. And that was somebody's job all day long. So that has gone away, thankfully. And even things like automated tests sort of have gone away. Huge automated test suites that cover everything in the software, every possible case, can't do anymore. We have 1-month cycles where we want, in fact, we have 2-week cycles. In 2-week cycles, you cannot run a 3-week test pass. We have tried, it just can't fit it in there. We've tried altering the speed of light, we've tried moving the test team really, really fast. None of that works, okay? And we haven't figured out the whole time travel thing yet. So we've got a problem there. We can't fit it in, so you get to run like 1 day's worth of testing. You got to figure out where that data is and what you're going to do with it. And that then requires you not to have these huge automated test suites. But the skills that we do want are the critical thinking skills. Testers tend to be very good at that. They also know how to break the software. So that means they're very good at creating a design of experiments. So they know all of the different cases that likely will break it. And then, of course, the programming skills we still have because we need to debug the software. So the testers become more and more involved in debugging as you get into less and less testing. So, as I look at a day in the life of a tester, there's really the three things then that test does. One is tools to gather data. So a lot of the telemetry data, a lot of building up these various tools for applying experiments to the code. That becomes a big part of test. Analyzing the data are in there, of course, that becomes a very important part. And that's really where the data science comes in, and your knowledge of statistics and machine learning and all the other fun stuff that go with the data analysis. And then finally, as I said, tracking down the root cause of problems. So this then is going to be what test looks like. There's really not going to be a whole lot of testing involved anymore. I believe test as a discipline where I'm going to run tests is going away and will be replaced with I am going to run experiments on the product and gather data on it and then use that data. So how do you begin to transition to being a data science? First, you start with the current strengths. As I said, we probably are all pretty good at DOE, even though we don't have a formal methodology for it necessarily. And we all have pretty good programming skills. And then start to add bits to it, like data management. So the data management difference between old school and new school is the data will be unstructured. So you need to start to be able to do exploratory analysis on it and build data sets that you can repeat it over and over again based upon various attributes of the data. From there, I'd like to add the probability and statistics first, because otherwise you start to do really bad things with your data. I've seen people produce really nice visual charts, and then the very first time you poke it, you figure out it's not statistically significant, so you've got this really pretty picture that really doesn't mean anything more than any other art hanging on the wall. So I always add that one first, and then move to predictive analytics. But that's the thing that everybody wants to do, because machine learning is kind of fun, and you get to play with all the fun algorithms. So everybody wants to jump to this one. Unfortunately, they jump to something that they're really not ready for. So I always put that one last. I also say, don't wing it, because you come up with some very strange things when you wing it. I've seen, like I said, I've seen some very interesting analyses which come up with some very fun answers that have absolutely no basis in reality. So the biggest change that we have to see is a mindset change, where we don't find bugs. That's not the job of test. The job of test is to find information. We might test in order to find the information, but the test is incidental. It's the information that's important. So information discovery versus bug discovery. That's the most important aspect change that I think that's going a lot faster than I thought it would. So I've been doing this for, let's see, I've been at Microsoft over 10 years, and I've always been a data scientist at Microsoft, even though my title didn't say that. And I've always done data analytics on it. And in the last 6 months, I've seen more progress in the last 6 months than I saw in the previous 10 years. So I think this is going very quickly. The other aspect that's important, and this is the one that's very difficult to get people to wrap their minds around, which is experiments are statistical in nature. They are non-deterministic. You run statistical experiments on a large population and pull in the information based on it. Okay, so you have to think large populations, not individual test case. That becomes a very difficult thing for a lot of people to do. They want to see something deterministic where they've controlled all the variables and they're looking only at a single variable change. If you can do that, that's great. I have never seen that done, ever. Okay, I've never seen a controlled experiment outside of a lab somewhere. So in the real type of experiments that we'll be running in the world of services, everything will be statistical in nature. You've got to start thinking statistically and probabilistically. There are some aspects of the old methods that are still there, but it's really all about the data now. It has nothing to do with the tests. It's all about the data and what data you can gather. And finally, testers will have to fix bugs. Okay, that's in my opinion, because you've got these agile teams working together, and you can't necessarily inject a new requirement in the middle of a sprint. So, but you might have to do a bug fix in the middle of a sprint, because a crashing bug requires a service to be upgraded the next day. You have to be able to do that. And only test is going to have that kind of skill to do that. So that's where I think it's going. And that's what I've got. Any questions?
So it sounds like you must get a lot of statistics or information in order to do any of this, right? So like you can't just do this with any product, right? I mean, you've got to have a web app or a service or something where you can constantly gather data from all your users and get the logs and everything, right? I mean, like imagine Notepad or something. How are you going to statistically test Notepad?
That's easy.
I'm curious because it's not like Notepad tells you every time someone starts. Right. You don't get to see all their keystrokes.
Okay, this is where more of the data science comes in. And this is also the reason I hate big data, because everybody thinks, oh, big data means I need millions and millions of observations in order to make it happen. That's not true, right? Give me the one right observation, and I'll give you the answer. So it's all about the right observation. And if you can do it in 1,000 observations instead of 100,000, that's even better. So that's part of thinking about the problem ahead of time and the research question. I talked about the research question idea that you're thinking about. So I know, for example, that certain things, like if I'm looking for bug arrival rates of a certain type, I know it's going to follow, as I said, a non-homogeneous Poisson process. And I'm going to expect that. That's a piece of information that I'm using. When the data start to come in, if they're not following that pattern, something's up. It's a bug. I know it's a bug. Okay. In the case of some of the stuff I've done, I can look at performance data. So I know the performance data of a particular set must follow a particular distribution. So there's something called a gamma distribution. I happen to know that a particular one of our features must follow a gamma distribution. As the data roll in maybe, I don't know, 20, 30 data items, I can say, oh, look at this. It has shifted the performance of the product over the last product by a significant amount. We have harmed the performance of the product. Then all I've got to do is go to the code repository, look at what particular code was added to the product and say, hey, your code harmed performance of the product by this amount. Okay, so I can look and know these certain things are true and make suppositions based on them. Okay? And there are quite a number of different types of processes that generate data. In fact, I would contend that all data come to us through some generation process. And that process has certain fundamental attributes. If you know those attributes, you can use them to your advantage, and then you don't need a huge amount of data. You can do it with a very small amount of data. Right. So with a handful of bugs coming, well, we have this thing that when your product crashes, if you've set up your system to send us that information, 5, 10 error reports, and we know what's going on. We know if it's significant, we know it's not significant, based upon these arrival rates. And hopefully what are supposed to be scarce events. So if the product is crashing all over the place, it's no longer a scarce event. So, but that's a completely different issue. For the most part, things follow these scarce event models, and you can depend upon that fact. And when they don't follow that model, information. So that's a part of the data science that has to start to happen for people to understand these underlying processes. And there's maybe, 4 or 5 that are important for reliability and analytics. Poisson process is probably the most important for us. Gamma distributions and Bernoulli processes, these are also the ones that are important. And I didn't go into what that means, but as data scientists, we have to start to understand what that means and then to apply our data gathering to that in that particular pattern. So that's why I said I hate big data, because small data, it's all I need. I really only need, if I got 10,000 observations, I probably have more than enough information to do what I need to do.
I hope this doesn't linger on, but like Donald Reinerson talks a lot in his book about proxy variables and so forth, that we're not really looking at root causes, and like we kind of see a parallel. We're looking at a correlation, but not really a real cause on something. How do you know when how do you discover that you're not looking at the right thing when you're doing your data analysis?
That I'm not looking at the right thing?
Yeah.
So, well, that's where, again, the science comes in. So I have to prove it. So I do proxies all the time. So I do a lot of proxies. So, for example, there's also this thing out there. The other part of being a scientist is there's, when you do like a dissertation, there's something called the body of knowledge. The body of knowledge is all of the experiments that have ever been done in a particular field and the theory that goes with it. So there's quite a lot of body of knowledge out there that we can depend on and we can start to use. And so I know things like that the total lines of code in the product will correlate very, very well. I shouldn't say total. The lines in a release that have changed, the new and changed lines of code, will correlate extremely well with the bugs in the product. Okay? We know that. Unfortunately, I don't know how many lines of code are in the product until I release the product, at which point it's kind of, I don't really care anymore. Right? So I create a proxy for the lines of code that are in the product. And there are lots of proxies that I can use. One interesting one is the amount of effort going into the product. I can measure the effort. I can use that to infer how many lines of code that will be. Okay. How did I come up with that? I ran the science on it. I measured the effort, I measured the lines of code, I did it over and over and over again. I looked at the probability density functions associated with those two different things, and now I have a model. I've done the regression on it. I have a nice regression model that says, here we go, if I measure how many people are working on it, full-time, part-time, etc., I have a good proxy for lines of code. I now know that lines of code will correlate to bugs in this sort of a way. I can make best estimates as to whether or not we found enough bugs. Now that's a little bit dangerous because I just sort of indicated that correlations are transitive. Correlations are not transitive. I've seen people try to use that. And so do not take this as correlations are transitive and you can do that. You actually have to do the science all the way through. So I've done it. I've gone and I've looked at proxies. So whenever I create a proxy, I create an experiment to prove that it is a good proxy for it. And that's where I've got a huge amount of historical data. So I can prove it in historical data and then make sure that my historical data are the same going forward as they were in the past.
So like say you make a proxy like you were talking about, prior to the release of the software, and once you release, you can actually say, okay, here's how many lines we actually have, here's how many bugs we actually found, and you can test out your proxy to verify it actually was right, or maybe your model was off.
Yeah, so in the last 10 years, I have an aggregate error of a little bit over 1%.
Wow.
So I know how many bugs are in the product it's probably closer to 2% now. Where I make mistakes are rare events. So I can build a model that will tell you exactly how many earthquakes there will be tomorrow. I can't tell you where they'll be, and I cannot tell you when the next big one will be. But I can tell you every day how many there will be. Okay, that's a very, it's big. It's a big number, right? But we can build models for that very well. Okay, so there are some bugs that I don't even want to mention the products because they make it to the media and stuff like that. But those are the ones that I can't predict. What I can predict is the aggregate and about the rate at which we will see them come in. And as I said, and that again goes with the fact it's a Poisson process. It's going to do something like this. I'll have a negative exponential. All I've got to do is integrate the exponential from time equals release to management to the end of time, and that's how many bugs are in it.
So my question is, I'm one of those people on the Venn diagram that doesn't have the third circle. All that stuff you just said about Poisson and negatives and doesn't mean anything to me yet. Where do you suggest is a starting point?
I absolutely love Coursera. Coursera, yeah, the massive online training program. If you haven't gone to Coursera.org, go there. They'll any course you want. Coursera is what I do instead of watching TV. I like it a lot, so I go home and I take a class in some bizarre thing, postmodernism, who knows. Every class you could possibly imagine is in there. I've taken everything from quantum theory to postmodernism, and it's literally true. And it's a college class, basically. And you can run tests and all sorts of fun things. And they give you the subject in like 5-minute chunks. So a 5-minute video on something, and you just go and you pick one. So in the case of statistics, I don't even know how many statisticals there are. There's probably, I don't know, maybe 36 universities that offer their courses up online. everyone has a course in statistics. It's probably the single most topic out there. But then there's lots of other topics. There's fun ones. So there's one of my absolute favorites is something on model thinking. So building models of reality. Okay, a guy named Scott Page from the University of Michigan. It is, in my opinion, the best of all of the Coursera courses. So you can learn things that are sort of off topic, but are very useful to you. And that's where I really suggest everybody goes to and really start every once in a while. Spend 3-4 hours a week, maybe at the most, and you can get a really good background very quickly. The deep ones, of course, that knowing the difference between why Bernoulli process is different from whatever Poisson process, those are very different. Knowing that takes a little bit more and a little bit more experience, but slowly you'll get there.
I was just wondering, what is the significance of R? What makes that stand out as a language?
So R is, it's actually an open source version of a program called S, which was all about statistics. And it's a really nice object-oriented environment. So as programmers, I like it a lot because I like object-oriented programming. You can do all sorts of fun things. You can program up your own functions. And somebody has probably already programmed something for you that does it. So
it's got tons of libraries.
Bayes model averaging, here you go. Here's a package on it. And then you just have to learn how to use the particular package.
So strength of statistics then?
Yeah, it's all statistics. It is specifically designed to do statistics. And then to do visuals too. And so you can very easily do exploratory data analysis, create histograms and box plots and scatter plots and all sorts of fun things. Quick linear models just to try and figure out what your data are telling you. Data manipulation is also pretty easy. Not quite as easy as Python, but it makes up for it by the visualization stuff.
And Python is using it as a shell around that or something?
No, Python's a different language. So
right.
Python is also a language. You can interact between Python and R these days. Python's great at data manipulation, so it's all about building dictionaries and manipulating dictionaries. It's really great at that. It also has the idea of packages, so there's lots of good packages for linear algebra. The downside is then you have to know linear algebra. So if you want to do a gradient descent algorithm, you have to do it using linear algebra and know how to do a second partial differentiation and stuff like that, which makes it a little bit tougher. And that's why I jumped to MATLAB in that case. But we will have to, as data scientists, get familiar with it. And in my opinion, R is the one to get familiar with because it's got the massive market share right now.
I missed the first part, maybe the first 10-15 minutes, sorry, I'm late. But as part of a test organization that as much of like data science as we get is probably like A/B testing and click-through rate or something like that, based on that, like how would you sort of start talking about using data for using data for testing in the manner you're talking about when we have like bug numbers we can look up or traffic or something like that. Like I think the part maybe where you actually figure like what data do you want to collect from like maybe at the beginning. But
yeah, well, I don't talk at all about what data you want because the data will come from the research question. So one of the other methodologies that I didn't talk about that I really like is a guy named Vic Basili, who created something called goal question metric, where you very step through to the metric. The metric is incidental. Everybody wants to jump right to the metric. Okay, this is what we'll measure. Well, why? Tell me what questions you can answer with that. And then once you tell me the questions, I'm going to say, well, but what goal are you trying to reach? So you do it the other way around. Start with your goal, figure out what questions you need to answer to know if you met your goal, then figure out the metrics. So I don't say these are what you need. So in your case, I would start out small, okay, because you can get into a quagmire very quickly. But something just like trend analysis on bugs. So build, over time, look at the trend analysis, look at the arrival rate of bugs. So I like doing Laplace trend tests all the time. It's one of my favorites for reliability analysis. So just start looking at what rate are bugs arriving. Okay. okay? And figuring out whether that rate is changing or not. So I keep mentioning Poisson process. It's very high in reliability engineering. If the rate is not changing, okay, that's a homogeneous Poisson process. If the rate is changing, that's a non-homogeneous Poisson process. If it's changing, figure out the rate at which it is changing, and that will then be able to predict when the product is ready. So you will know we have to do this much testing until we get to a point where we have few enough defects that people won't notice them. So just starting to do the trend analysis is a really good first step. And it'll also get you used to time dependencies in your data, which are very tricky. So while it's simple to do, it also gets you used to some very tricky analytics at the same time.
So maybe it also involves, well, of course, adding skills, but maybe hiring people that know this right off the bat.
Yeah.
Know,
Find yourself a theoretical physicist. That's always good. They make the best data scientists.
$30 an hour.
Well, yeah, you're not going to quite find them for that. But
Yeah.
either that or biostatistics. Also, we've got several people who have degrees in some different types of biological sciences. There's actually some really good similarities between software development and bioanalytics, which seem kind of like an odd thing, but it turns out it fits right in. Any other? Okay, well, thank you all very much.
Thank you.
Thank you, Bob.
Sure.